factor lambda, or this is the this lambda. It is dependent upon on how you apply load and also the geometry of the specimen you are using. So this is based on the geometry and the load you have, and you select the appropriate lambda. I need to tell you, so this is just empirical. If you want to get very accurate results, you need to do the experiment special of 4, and you need to do using IBM to do the numerical simulations. Then we talk about this is this is a criteria for Dalton material. We only emphasize so these 2 series. One is MSST, one is DET, and we had a problem in exam 1 already. Then I give you example for this one to illustrate how to solve the problem, and then we are going to talk about a problem and what if we have a crack. Okay, so what if we have a crack? If we have a crack, and how to solve the problem? So for this problem, and let's use this. So either way will be okay. Let's focus on this one. For this is a 5.6. 5.6 and says that we have this geometry, and we have this is the crack. So you can see the crack is not located in the middle, and it has some deviation from this middle. So we have a D here. Okay, so the geometry is all the geometry is given, the parameters are given, and D, B, and 2A the crack length, and 2B this is the width of the specimen, and so they have these ratios. Okay, so whenever you see this kind of the crack, which means that this is a central crack, but this crack is not in the middle of the specimen. So the B plays an important role also. So you need to, based on this is A and D, based on this value, DB ratio B over B and ratio of A over D, you can just select this is a curve. Okay, select a curve. But for this one, B over B equals 1, and you just select this one A over D. Okay, so this is A over D equals this one. A over D is so small, so on the beta you can select beta equals 1. So this is a beta. So the beta equals lambda. Okay, beta is a geometry correction factor, and so some people use the lambda, some people use the beta. They're talking about the same thing. Don't be confused. All right. So you can look at this here. This figure, and we have beta here. But for the several of the figures I presented, I use the lambda. And as I said, and these 2 guys are talking about the same thing. The geometry correction factor, and for the stress intensity factor. And then you can just use this equation. The Ki, and Ki is sigma square root of pi A, and pi A is a stress level, and you have, and A is a crack length. So because of beta, actually there should be a beta here, okay? Actually there should be a beta or lambda, but because A over D is too small, so beta equals 1. We just select beta equals 1. See, A over D is very, very slow, and you select 1.0. If A over D is kind of big, for example, was 0.8, and you need to draw a vertical line here. And so this vertical line will intersect until this P over B is curved at this point. So if the A over D, the ratio A over D equals 0.8, and you draw a vertical line, and this vertical line and will intersect so this curve, which B over B equals 1. So here, then I draw a line here. So this is a beta will be equal to 1.8. So it's almost a double. Okay. So you should know why here we do not have the lambda or beta, because beta equals 1. Questions? No questions? Then we have to look at this Ki and we just compare the KIC. The KIC is a material parameter. It is fixed if you select after you select a material. If you want the KIC is a new one, that means you need to have a new material. KIC does not change if you keep using the same material. So then you can use and KIC is a constant for the same material, and Ki is dependent upon the loading condition and geometry. And so based on this one, you can calculate, and this is the safety factor. Okay, and then stress at which catastrophic this is failure occurs. Catastrophic failure occurs means that this is NKI equals KIC. You understand?
What is meant by catastrophic failure?
Catastrophic failure means that so the crack is going to propagate. If the crack is going to propagate, that means you have no control. Right? If you have no control, that means so this crack initiates and then crack propagates until the whole thing the break. So see here. So this is NKI equals and KIC. So this is if this is a equation holds, that means the catastrophic phenomenon occurs. Right? This is critical, but we do not want so this equation hold. And then so this is a Ki, okay? So this is I said, and KIC is a material parameter. It does not change after you select the material. And N after you have this N here, okay? After you have this N stress intensity factor. So how to calculate this N, this Ki and equals and sigma pi squared. So the beta equals 1. The beta equals 1. So it equals sigma and pi A, and you just want this guy equals your KIC and divided by and this is N. Right? So here, so this one will be your sigma the maximum. So this you can see the sigma maximum equals KIC and divided by N, and then if you want to use 1.77, and then just the square root on pi A. So this is the maximum sigma and you can have. Understand? So usually we select a safety factor and that is higher than 1. Questions? No question? No question for the this one is very similar. I want to give this one to you guys, right? So you can just take a look. And then we talk about this is a static loading. Static loading, I will talk about the ductile material, the failure criteria, the MSST and DT, and then we talk about this is the first stop. This is fracture mechanics, the based method, and then we talk about this is cyclic loading. And cyclic loading is more important and also more dangerous. We talk about cyclic loading. So here are today's objectives, and we want to know the concept of fatigue, strength, and endurance limit. Do you have idea about the fatigue? You know fatigue, right? Okay, and so learn how to use the SN. SN stands for stress, and N stands for the number of cycles. Write down it. S means the stress level you apply, and N is the number of cycles that you can have before this specimen fails. And this SN diagram to compute the fatigue strength, because it is a strength. And when the number of cycles is given, and we want to learn the influence of non-zero mean stress on the fail, and then we learn different failure series and predicting the the fatigue failure. So fatigue is very, very important. It is much more dangerous than the static loading. Why? Because you can see the static loading and with the stress intensity factor, the critical stress intensity factor is involved, and also yield strength is involved. But for the fatigue, the things are different. What is the fatigue, guys? You can see. So when you guys were young, have you guys ever played some specimen? That's the back and forth, and finally it breaks. Have you guys played? Have this kind of game? When I was young, I have these things. A little, this is the wire, metal wire. I just bend this way. Finally it breaks. Yeah. So you can see why fatigue is very, very dangerous, because the fatigue is depending upon how many times you have applied the load cycle, back and forth. And even though the stress level is much lower than the yield strength of the material, however, as the number of cycles increase, and then this fatigue will occur. Understand, guys? For the static loading, we compare this is the stress level with the yield stress level, and we all compare, and this is the critical intensity stress intensity factor, and this is the actual stress intensity factor. But for the fatigue, the number of cycles plays an important role. The time plays an important role. So even though the stress level is very, very low, as long as you applied this back and forth cyclic loading, finally it will break. So also the fatigue is very, very difficult to discern. If you do not pay attention to it, and sometimes it happens. But as a responsible mechanical engineer, when we design anything, we need to consider these loading conditions we might have. Okay? If the loading conditions is a kind of cyclic, you need to do the fatigue analysis before you fabricate the material, fabricate the structure system. Questions regarding this one? What I might ask you guys, use your own words, tell me, and why the fatigue is important and why fatigue is more dangerous than static loading. Right? So the key point is that the number of cycles plays an important role. And even though the stress level you apply is much, much lower than the yield strength. However, as the time goes, as the number of cycles increases, it will break. These are three stages of fatigue failure. Fatigue, whenever this specimen, no matter how well you have manufactured it and how smooth you claim the surface is, because we still have some cracks on the surface. So first stage is a crack initiation, and we just assume the cracks and they are present. And then we assume the size of the crack is equal to actual the crack length or the capability of the NDE. NDE means that non-destructive evaluation, right? Non-destructive evaluation means that we have some means to detect the cracks in the specimen. Non-destructive means that you do not need to cut it, okay? If you cut it and then tell me, hey, there's no crack, but you already ruined the specimen. You understand, guys? That's called non-destructive evaluation. So second stage is a crack propagation. The crack propagation is following a very, very smooth curve, and this is called the Paris law. The crack propagation, and it follows the crack Paris law, and this is the Paris and Paris law. About Paris, it's a Paris law. Paris law is this equation. We can use an equation to describe the crack propagation, and we are going to talk about this equation. Have you guys ever learned the Paris law, guys? No? Okay, it's a new thing. So third one, also the last stage is a fracture. After some time, and the crack is going to evolve very, very quickly, just like the brittle like the fracture, just like cleavage, very, very quickly. So this will be very, very dangerous stage. Questions regarding this slide? No question? So methods to maximize design life. And we have the commonly used methods. Okay, so this is the first one. The design life means is talk about the fatigue life. This fatigue life is a very, very important component of design life. So how to maximize design life? There are four means. The first one is that minimizing the initial flaws, the defects, and especially service flaws. So why? Because if you have a flaw, right? I have a lot of flaws on the surface of small cracks, and when you apply the cyclical load, these cracks will be close, open, close, open, close, open, and it will propagate. So this one is for fatigue life. And second one, maximizing the crack initiation time. So I have talked about the 3 stages. First stage is crack initiation. So I just want to maximize the crack initiation time. How to do that? So the surface residual stress, okay? So we do the pinning. I told you guys, this is the compressive residual stress is beneficial. So we can just use a short pinning, or this is a burnition. Burnition is used another roller to cold work the material, or by a number of surface treatments. But this one is want to maximize the crack initiation time. We want to induce this is a compressive residual stress on the surface. So the third one is maximizing crack propagation time. How to do that? The material, if the crack is propagating, and how can you maximize the time it takes? And you can see substrate properties, especially those that retard crack growth, are also important. For example, predicted cracks propagate more quickly along the grain boundaries, right? Along the grain boundaries than through grills, because grains have much more efficient atomic packing. Thus, using a material that does not present elongated grains in the direction of the fatigue crack growth can extend fatigue life. You can see, and for this is third means, and we are talking about the microstructure. You understand, guys? I want you guys to follow me, right? Follow me closely. After class, you don't need to do anything. If you are working on something else now, after the class, you need to review. This is watch the video, and then you use the double time. So lastly, maximizing critical crack length. This critical crack length, that means I'm talking about material. So that means fracture toughness is essential ingredient. And fracture toughness is a material property. That means for this one, that means I'm using a better material that has the fracture toughness, a bigger fracture toughness. Any questions? Okay, so you need to know, okay, if I just give you a conceptual question and tell me the means that we have and to maximize design life. This is what I'm talking about. And then we talk about the fatigue loading. Fatigue, as I said, fatigue is under the cyclic loading. So we have 3 case scenarios. So for first one is a fully reversed. You can see the stress level. And the stress level, I just for example, I bend that this is a little wire or this little rod. Back and forth. You can see maximum sigma and minimum sigma. Okay, so they are opposite, but in magnitude they are the same. So as a result, the mean stress, sigma m means mean. Mean stress is the average between the heaviest one and lowest one. And sigma m equals 0. And for if this condition holds, and we say this is called fully reversed. What? Fully reversed. And second one is much worse, okay, in terms of fatigue life. Why? And because I have the stress, and even my lowest stress level is almost a tensile. As I told you guys, tensile stress is bad. Why? Because tensile stress is going to facilitate the propagation of the cracks on the surface. So you can see this is a sigma. This is sigma m. This is a sigma m. Okay, this is a sigma m. So this is a sigma a. Sigma a is sigma a is divided by delta sigma divided by 2. So delta sigma is the range between the maximum and the minimum. And sigma m is the average of between these two lengths. And so these are repeat. So the third case is much worse, the worst one. Why? Even the minimum stress level is also a tensile. Tensile is bad. Whenever you apply a load, a tensile load, you need to pay more attention to the particular. Any questions regarding these three case scenarios? Free reversed, repeated, fluctuating. This one is the worst. Questions? No question? And then there are several concepts. The first one is the stress range. Stress range one is, as the name suggests, and it is the range between this is a sigma. That means maximum minus minimum. And sigma is called amplitude, or this alternating this component. Alternating component equals half of sigma maximum. I prefer to write this way. Okay, so because sigma a and sigma a equals half of sigma maximum minus sigma minimum alternating stress level, and sigma m equals sigma maximum and plus sigma minimum, which is the average level of the stress. So this is, we are going to use these two very, very often. They are the most important two concepts and two values to determine the fatigue level of your components. Questions so far? We also have amplitude ratio. So actually, this is the derivative from there, the stress ratio. Questions so far, guys? No questions? So this is alternating component and means component. I want you to be very familiar with these two concepts. Then the fatigue, the crack growth. So this is you can see delta sigma. Delta sigma is a stress range. Okay, delta sigma is a stress range. So for this one, for the second case scenario, the stress range is much lower, much higher than this is the first case scenario. So this is number of cycles. This is crack length. You can see. So this one will go very, very fast. It's go very fast. So DABN. A is a crack length, and N is a number of cycles. So this one, so second case scenario, the specimen will be filled much more quickly than the first one. You understand? It's understandable, right? The load, if the range is bigger, definitely it is easier to be filled. So this one shows the stress crack growth for the three stages. First stage, crack initiation, and second stage is called this is Paris law Gauss. This is the second stage, and after the third stage, it goes very, very quickly, just like this is a failure. That's a cleavage. Cleavage goes very, very fast. So this line, you can see, this is a natural. This is not natural. This is a common law. This is a common law. This is a crack growth. DADN. You can see this one is almost a straight line, right? It's a straight line. So this equation comes from here to here. So this is called the Paris law. So this is called Paris law. Paris law tells you how the crack length increases as the number of cycles goes. So this is C and N, and they are material parameters. So delta K, right? And delta K, because our stress level is changing, right? We have delta sigma, and we have delta sigma, then we have this delta K. Delta K is a change, the range of stress intensity factor. Because your sigma is changing. One sigma, the big one, when you have the maximum sigma and you have maximum stress intensity factor. When you have a minimum sigma and you have a minimum stress intensity factor. Because your stress level is changing as a result, and your stress intensity factor is changing. Kevin.
So like, I know like N means the number of cycles till failure, right?
This is lowercase.
Yeah, it means like the number of cycles till that material fails, right?
Yeah.
So like, I guess my question is, what is one cycle? Like, how do you know when one cycle is completed?
One
Does that make
cycle.
sense? Is it like when it like bends and it goes back, is that one cycle?
Yeah.
Okay.
Yeah, if we back and forth, this is one step.
Okay.
Back and forth is one step. Good question. Questions? Okay, write down this. I want you to write down. This is called Paris law, and we will. I will test your understanding in our second exam or this midterm. So there are two categories. One is called low cycle, one is called high cycle. And the low cycle means that this is the number of cycles is lower than 10 power 3, 1,000 cycles. So 1,000 cycles is a magic number. So if the number of cycles is greater than 10 power 3, and we call high cycle, is this the failure. And then we talk about fatigue strength of ferrous metals. Can somebody tell me what is a ferrous metal?
Metal that contains some kind of iron.
Yeah, when ferrous metal means we have some iron in this one. So why I talk about this one, because of ferrous metal and non-ferrous metal, and they behave totally different, So in terms of fatigue, so you can see, okay. So this is the number of cycles. This diagram is called an SN diagram. Stress, this is stress. So this is the number of cycles to failure. You can see. So this is the dot. These are dots. These are empty dots. They represent the experimental data. The experiment represents the experimental data. So you can see for this different, we have this material. Nominally, this material, these specimens, they are of the same material. But when you do the experiments, and you will get some different. This is some variation of this is the results. So number of cycles and failure. This is a failure stress ratio, and this is S ultimate. Ultimate means ultimate strength. Can we write down S? SUT means ultimate strength. SUT means ultimate strength. And so this is SF. SF is a fatigue stress. The fatigue stress you are applying. So because SUT is constant, and when actually this is just a normalization of this is SF. So you can see, right? To be conservative, and we just use this curve. We just use this boundary. We have two boundary lines. And to be conservative, and we just use this is the lower the boundary line, and you can see there's a horizontal line here, okay? Horizontal line here. So here is the 10 power 6, 1 million cycles. So 1 million cycles is also a magic number. You can see here from here, so this will be horizontal. So this one is called stress. This is called endurance limit. Fatigue endurance limit. So this one, okay, I want to tell you guys, So this value, this stress level is the endurance limit. Endurance limit. So endurance limit is denoted using SE. SE, endurance limit. Endurance limit and the physical meaning of physical significance of endurance limit is that I want to guys to listen, okay? The physical meaning of this endurance limit means that if you apply a stress level that is lower than this endurance limit, then theoretically, I use the theoretically, no matter how many number of cycles you apply to this specimen, theoretically the specimen will not fail. One more time. And the physical significance of stress endurance limit is that if you apply a stress level which is lower than the endurance limit, then no matter how many number of cycles you apply to this specimen, your specimen will not fail theoretically. Why I use theoretically? Because sometimes this is not the case. Because when you manufacture this is a specimen, there's some unpredicted failures, some the defects. But theoretically is the case. Questions? Okay, so endurance limit is a material parameter. It's a material parameter. So you can see here. So this is 10 power 3, right? The 10 power 3. So the 10 power 3, I have a point. On 10 power 6, I have another value. Another value is endurance limit. If I have endurance limit, also I know the stress level, and this is the number of 10 power 3. So I can use the two different points to determine this straight line. You guys agree? Right? So if we have two different points, and we can use a straight line, and between these two points, we can define a unique straight line. You guys agree? My point is that my assumption is these 2 points, they are different. If we have two different points, and we can connect these 2 points using a straight line, and this straight line is unique. And you can only have one straight line, you cannot have a second one. You guys agree? So I have 10 power 3. You can see I have 10 power 3. And 10 power 3 and corresponds to this is SL prime. SL prime. L. This is SL prime. And 10 power 6 and corresponds to the SE. And we use SE prime, okay? SE prime. And the reason is that we have another, so SE prime is a theoretical one. So 10 power 3, we have SL prime. SL prime is a fatigue strength. And fatigue strength at which the high cycle fatigue begins. High cycle of fatigue starts. And high cycle fatigue starts means that this is 10 power 3, right? Number of cycles. So SE prime is the theoretical endurance limit. we have theoretical and actually we have the modified. Modified means that we take care of other factors. You understand, guys? So what I'm teaching you now is the most important thing for the particular line. So I have 2 points, 10 power 3 and SL prime. So these 2 guys are the coordinates of my first point. My first point is here. And 10 power 6 and SE prime, I have a second point. And based on the 2 different points, I can have a straight line, right? So I can write this as a straight line. And this straight line is a straight line as what I want to tell you is so the BS and BS is the slope. And BS is the slope of this straight line, and BS equals -1/3 minus 1/3 is the common law. Make sure this is a common law, guys. And it S L prime divided by SE prime. Right down. So also pay attention to this minus sign. If you forget this minus sign, I'm 100% sure your final answer will be wrong, right? Yeah, it's understandable. It is the minus sign. Also, here is a common log, not a natural log. Natural log is ln. Here is a common log. That means the base is 10. I have this BS here. Okay, after I get this BS, given any number value, given any number of values here. So given number of cycles, billion. So given number of cycles to failure, I will have a unique number, right? Given any number of cycles to failure. For example, here, I can just draw a vertical line, and this vertical line intersects. So this is a straight line at this point, and then I just draw a horizontal line. Right? This horizontal line is ordinate, is new ordinate. This new ordinate is the fatigue strength. If you want this number of cycles to fail. Understand? So NT is the number of cycles to failure, and the corresponding SF prime is fatigue strength. Fatigue strength. So because I have BS here, then you can see ASM prime equals NT prime and power BS, and then multiplied by SL prime cubic and SE prime. So what does this equation say? The equation says that if I know the number of cycles you want, okay, and then I use this equation, I can calculate the fatigue strength you have, or the stress level you need to apply if you want to have this kind of number of cycles to failure. You understand? So this is one direction. Another direction is I have SF and how to calculate the corresponding number of cycles. And so this one is using this. NT prime equals, on parentheses, SL F prime and S L prime square multiplied by S E prime parentheses, the power is 1 over BS. See, and this equation says that if I know the fatigue or the stress level I have, I can use this equation as L prime, see, as L prime, as E prime, and they are dependent upon the material. And then I using this equation, I know the number of cycles to failure. That means the fatigue level of this material. Questions so far? No questions? So based on my prior teaching experience, so some students just ignore this minus sign. Ignore minus sign, that means all your calculation will be wrong. And then we talk about SL prime and SE prime, and how we define the SL prime as SE prime. So they are based upon the bending conditions. So for bending, and for axial loading, and for torsion, for different loading conditions, and we will have different equations to calculate SL prime and SE prime. And for SE prime, for bending with SE prime and equals at 0.5 SU. And so this is SU or SUT, they are the same, ultimate strength. So the SE prime equals 0.5 SU, and SL prime equals, so this L, okay, SL prime is 0.9 SU. So for this for bending, I want you guys to write down. And for axial loading, and so this SE prime equals 0.45 SU, and SL prime equals 0.75 SU. And then torsion, SE prime equals 0.29 SU, and SL prime equals 0.72 SU. You can see different loading conditions, and we will have different vectors for SE prime and SL prime. And so some students might ask, Doma, and what if for our actual loading and we have a combination of these three rays? And we just use the dominating one, okay? I'm going to tell you in our test, I'm going to tell you what we use. Understand, guys? Using dominating one. So for example, with the bending load is very, very much higher than the axial or torsion, and we just use this one. And similarly, if the axial loading is very, very high, and we use this one. The torsional loading is very, very high, much higher than these two guys, and we use this. Have sense? Okay. Now, so this is the most important things I want you to have. Now I want to ask you guys. Can you guys close your eyes and tell me what is the endurance limit, the physical meaning of endurance limit? Can somebody volunteer? Ready?
Physical meaning of endurance limit is the stress that you can put it on, the stress value that if you apply a stress under it, then it theoretically should not fail no matter how many cycles you apply on it.
Yes, great. Okay, thank you. So once again, so the stress intensity, so this is endurance limit means that if the stress level you are applying is lower than this value, theoretically, no matter how many numbers of cycles you apply, to this material, to this specimen, and theoretically this specimen will not fail. Why I use the theoretically? Because when people build this is a structured material, they have some unpredicted inclusions, the surface fractures, defects. Okay, all these bad things will affect the particular. That's the reason I use a quotation mark theoretically. That's very good. I want also you know that this is SN diagram. That is called SN diagram. And if the stress level is given, and how to calculate the number of cycles. Also, if the number of cycles I want is given, and how can I calculate? And this is actual stress level using these two equations. Okay, and that's all for today. And afterwards, I will want to go one thing.